Okay, welcome back. Last time we were taking a look at this, and main thing here is kind of looking at conservation angular momentum on moving and fixed reference frames. So at least the way that I kind of think about this problem is like, it's like a pendulum on a table, like a 2 degree of freedom pendulum. It can swing X forward, backward, move around in a circle, and the table's moving away, and you're watching this whole thing happen. So far we've defined kinematics, and when we define kinematics, we're just choosing a coordinate system and identifying degrees of freedom. Like what are we actually calling like the degree of freedom, r and theta in this case. Then based on that kinematics, we can say like, okay, position is now our radius along one unit vector, and then velocity is going to have 2 components along that, ER and E theta. And then the last step is last step that we got to last time was a free body diagram, and that one's our kinetics, like just describing what's causing motion. So the cause of motion and the actual like describing motion. Those are the 2 things that we've done. From here, the last step is like our F equals ma. Like if we know what the motion is and we know what causes the motion, then we should be able to relate the 2 and get some kind of equation or like something that's unchanging along the way. So that's kind of what we're looking for. In dynamics, and I say this a lot, but dynamics is weird because a lot of this stuff is changing, but you're looking for what's constant. Kind of like thermodynamics. It's like you don't know what's going to happen, but you know energy can't change. You can't get free energy. This is similar. It's like you don't know exactly how everything's going to move, but you know that F equals ma, and that's what we're doing here. All right, so I think, yeah, we have our free body diagram. So we're done with this part. Now we want to define angular momentum. What is angular momentum? Do we know how to define that? Let me rewrite the stuff that we have. So we define position, we define velocity. They're kind of like, at this point, they're just general definitions. It's just like, if something's moving, this is how we describe position velocity. Yeah?
Oh, sorry. Is it R times MV?
RMV? Does that sound right? Is that angular momentum? The units work out. Like, we need some kind of distance and we need some kind of momentum. So, like, if you think about linear momentum, it's a kilogram times a meter per second, like m times v. Angular momentum is going to be kilogram meter squared per second, so there's going to be some extra distance there. Is this all we need? R and v?
Maybe we need like a theta in there because it's angular and how much things.
Yeah, should there be an angle? Should there be angle in here? Maybe? Does momentum, here, let's do a quick.
I guess what matters is you mentioned the velocity and stuff like that.
Here's a momentum moment for us. Mass times velocity. Is this a scalar, a vector, a matrix, fourth dimensional tensor? What do we think? Scalar, vector, matrix? I mean, we could just call it a day and say it's a tensor of some unknown dimension, but we haven't gotten there. Vector? Yeah, mass is a scalar. Like, it doesn't matter how much mass you have. It's a value, whatever. 100 pounds is a little weird because technically pounds is a vector because it's a force, so it's like a vector towards the Earth. But mass, how many kilograms you are, that one is scalar. Velocity is a vector. So this is a vector. What do we think about h, angular momentum? Scalar, vector, yep. Should be some kind of vector, right? It should have some scale, like how much angular momentum, and it's got to have a direction. Yeah, so what is the direction of, if we have angular momentum, which way is it pointing? Yeah. Ooh, a cross product? Oh man, you like jumped right to the conclusion. So it's a cross product of what? What's the cross product? Of vectors? Okay, so it's some kind of cross product. So it's a cross product. So if I'm spinning around, like I have angular momentum, right? Which direction is my angular momentum pointing as I spin? Up? Straight up? But I'm spinning this way. Yeah? Is it tangent? Like, so my thumb is my angular momentum? So it keeps changing. It keeps changing direction. Where is it pointing? Around? Yeah. Right hand rule, right? Yeah. So it's pointing up in this case, because if I take right hand rule and twist it around, it's got straight up. We have angular momentum pointing right up. If I spin the other way, it's straight down. So that's our angular momentum. Is kind of weird because it's describing the axis of rotation. Like, what is it rotating around? So if I come back to this equation, just take the radius, multiply it by mass times speed. Is that all I need? I mean, this would be a scalar value because radius is a scalar. It's just describing how far away I am, a distance. And then speed is also scalar. But there was this idea of a cross product that came up. Which one? Oh, nice. Vector cross, position cross velocity. I like that. All right, so we'll take this same thing and we'll just turn it into a vector product. So we're doing cross product of position with momentum. Thanks, Jimmy. What do we think? Do we know where to go from here? Or keep? You want to watch me keep spinning like a whirling dervish? All right, try. Because now at least we have a definition for angular momentum. And really right now, all we're doing is applying definitions. We're not solving an equation or anything. It's just taking what is the definition of angular momentum? How does it apply to this problem? That's what we're doing. So how do I apply this definition? Give it a shot. I'm going to see kind of where people are at. Different people, I don't know the last time you've taken a cross product. It doesn't come up a lot. It's not really like a Halloween sort of thing. It's a little scary, but it doesn't come up very often. So give it a shot. See where you're at. I also like to see how you do it. Yeah, exactly. Yeah. Great idea. Yeah, have you done cross products before? Do you remember? Okay, yeah. All right, yeah. So in this case, if you use that ER, E theta, K,
Yeah,
those
so,
three,
yeah,
top
that's
is
what I
right,
got,
or the top
right.
row.
So.
Yeah, and then this would be R.
Oh, my God. And then this we did it up.
Yeah, so we have that R theta.
All right. Will this be R theta?
Yeah, the R theta.
This is exactly. And then here, this. That's cross product.
Okay. Are you putting it into cosine sine B1 and B2s? Yeah. For sure. Do that. It takes longer. You can do it. You'll end up in the same answer either way. This one's easier just because it only has one component. Okay. What is it? Not the second. I think you should do it your way. The challenging. More vocal. Yeah, where's that? Yeah, exactly. And then do you use determinant to is that what you're trying to do? Yeah, like that first row is usually unit of these. So usually we write IJK, you want B2, B3, but in this case we have ER, E theta, and they're the same thing. So ER, E theta, K is the last one.
Most likely an array.
You'd like the array format?
Yeah.
Okay, yep.
So I actually believe you're out of grade from one of my projections, and then just getting used to the array.
Yes. So with the determinant setup, you're trying to do a 3 by 3.
Yeah.
First row.
Yeah, E times 1 is 2
Next row.
I don't know how. Okay.
All right, so most people, at least from what I was walking around, and we could take, the M is that mass, you can put that wherever you want. It's a scalar. Like taking the cross product of a scalar with a vector is just multiplying it. So we can put it wherever we want. I'm gonna move it off to the side, and then we'll look at the rest of the cross product. Does anyone have like issues with that, what I wrote here? That's where I saw most people kind of starting and then Googling what is a cross product from there and trying to figure out like, I know I've done this before. Yeah.
Why is that M not distributed on the second velocity?
So because M is not a vector, I can move it anywhere I want because it's just like adding some mass to that R cross V. I can't switch the V and R because that'll be the negative cross product, but I can move the mass wherever I want. So I just bumped it out.
So it doesn't matter if you had like distributed it in terms of the velocity vector, you're gonna get the same.
Like if I had left it over here, well, I would still have an MR dot and an M here.
Yeah.
So I can just move it, or I could leave it out here and say MR, or I could pull it all the way out. Yeah. Yeah, that's a good question of like where can you move? And for the most part, if you're doing cross products, take that mass, put it wherever you want. A lot of times, like physicists will like get rid of mass completely and have like angular momentum per mass. It makes the math a little easier sometimes, but we're engineers. We'll leave the mass there. Angular momentum still has, so the units always work out. All right, this was where I saw most people going for their next step of like, I know it's a determinant, you just need to determine the determinant factors, something like that. Is this how you learned cross products? All right, we can do it this. We'll start this way, then I'll show you what I think is easier, but start this way. All right, first row is just our unit vectors. So what unit vectors do we have? Yeah.
E R, E sub R, E sub K.
Is that it? E sub T, yeah, something. K, we could call it B3, we could call it A3, we could call it K. It's something that is perpendicular to ER and E theta, so it's up out of the page. I'm gonna write B3. Not to say that that's better than K, just because we have a B1 and we have a B2, and we've been talking about the B's, the birds, the bees, the cylindrical coordinates. Then the next row is vector 1, and then the last row is vector 2. So our first vector only has r in that ER direction. And then a 0 and a 0. And again, this is why I like to write positions and velocities in terms of like unit vectors. So theta doesn't show up in my position. Right? Like theta's already baked into my unit vector. I don't need it to describe where the thing is. Now I have r dot, r theta dot, and 0. How does this look compared to like previous stuff? All right, give this a shot, see what you come up with. I'm gonna do it a different way and we'll compare the answers. Sound good? All right, so we'll all take 30 seconds, do a little bit of math, and then we'll compare what we got. No rush. Just give it a shot.
Something different? Okay.
Well, I did that one across the board.
Yeah, so here,
It's like this across this.
let's start up here. Your ER term is going to be ER 0 times 0. That one's E theta, you're going to say 0, okay, 0 times R. You kind of rewrite this twice. These two columns out here. But 0 times R, still 0. Now my K term is going to have a R times R theta.
Oh, yeah, now it's, no.
Yeah, and then you subtract.
So I was doing like ER. This.
Yeah.
Yeah, cross out the row.
Yeah. Go like diagonally down.
Slowly coming back. That was a rough class.
Yeah. Yeah, the first time it makes no sense. By the second or third time, it's
Yeah.
I think I got it.
It just takes some practice. But I haven't. I do see how it's like a lot. There's a reason it's called. Yeah. It's like.
Okay. Yeah. That one, I like that one better because even if you're mixing and matching unit vectors. Like ER crossed with E1.
I just like to see what motivation.
Yeah, yeah.
To get through the model.
Sort of
Harder. Yes. Something drew us to tables. Yeah, how's that one? What are these fits here? Oh, I see. But the determinant. Yes.
It's drawers that they much square. Much square. They be creative.
Yeah. So it looks like we have to see that.
Be like determined.
Yeah.
So what's the actual difference?
I didn't see anything that would go against like my little box dancer. So I did it this way just because this is the way I always do cross products now. I used to use determinant method. I used to be just like you, sitting in the class using my determinants. But I like this method of, because now I can kind of just look at unit vectors and the scalar stuff. I can separate the two, right? Like it's not all one big jumbled mess of stuff. And I know an ER, like a vector crossed with itself, like pointing in the same direction, it's got to be 0. Meanwhile, like two orthogonal vectors, it has to be the third vector. So I usually write down this little reminder of like, if I'm going clockwise, it's positive. If I'm going counterclockwise, it's negative. Didn't really come in handy this time, but ER cross E theta is a positive K, not a negative K. Or B3. I wrote B3, but then I used K. B3, there we go. So here's a question. Or question. Yeah, what do I want to say? Is this angular momentum, would it be different if there was a different force applied here? Like that would cause different changes, but with the definition of the definition that we just made, would that change? No. Because all we really did was take a given cylindrical position and a cylindrical velocity, take the cross product. So if you're in cylindrical coordinates, this is always this is a statement that's always true. We kind of just like mr squared theta dot is always a point mass moving in a cylindrical coordinate system. And that part's kind of cool. Like do something, it's specific for this problem, but it's always the same definition. Like we could have looked it up somewhere and figured it out that way. So I'm trying to do one step at a time. All right. So E is really kind of two parts. We want to look at what is, so we just derived what is angular momentum in O prime. Then we also want to see what is angular momentum, or like what are the changes in angular momentum in O. So it's kind of two parts to this, if that makes sense. Give me back my pen. Sorry, I'm just reloading. Oh my God. Why? Every time. We're on a roll too. Come on. Am I out of batteries or something? Wait for a second. There we go. Try a new battery. Do you remember this equation, or does it ring a bell? Sum of the moments is change in angular momentum. This one, really, it's just restating Newton's law, because sum of the moments is R cross the sum of the forces, which is equal to R cross, really it's MA, but we'll just write it out here. And there's like a derivation that we could do, but for the most part, like R cross F is R cross MV, the change in R cross MV. If you're worried, there is like an extra term in there, but it cancels out to 0. So that's what we're doing here. What are the sum of the moments around O prime? How much torque is there around O prime? Yeah. see a 0, Jimmy. It's either 0 or infinity, right? Those are always the two answers. Why 0? Why would it be 0?
The only force is radiating, right? So there's no torque.
Yeah, we have one. So if I take the position of P with respect to O prime, that's RER. That's my position. Crossed with, I could call it like KR. Really, it's a negative K. Negative KR ER. It's got to be 0. ER cross ER has to be 0. Does that mean angular momentum has to be 0? No? The change is 0. Okay, all right. So if the change is 0, angular momentum constant. No change in angular momentum. So sum of the moments around O prime is 0, which equals mr squared theta dot. So we're saying, like, once we have some spinning motion, it's never going to stop around that. At least based on our current free body, like the forces that we included, there is no stop to this. It's just going to move around in this ellipse, and it'll do that forever. And that's what we see with like the sun, the moon, the earth around the sun. Like, it's in this orbit, and the orbit's just not stopping because there's the only force is an ER kind of force. We can change, like if we get closer, if R decreases, theta dot has to go up. If R increases, theta dot has to go down. So the further out you get, the slower you move, and the closer you get, the faster you rotate. Cool? We can kind of approach this in two ways. What's the sum of the moments around O? Or we could look at what is the angular momentum around O, whichever one you want to do. Which one do you want to do? Moments, momentum, momentum. All right, momentum's fine. So I'm going to rewrite our RPO was V0T B1 plus RER VPO All right, what is angular momentum around O? What is that? Forgot my hat. Can't go outside without a hat.
Yeah, would that make the matrix provide E theta, B1 theta, B1.
Oh, yeah, can we just add an extra column to our thing?
Not for one
It's too much.
Yeah, can we say B1, ER, E theta, and B3?
I don't think that's right.
No, yeah. I like the idea of just like, well, there's an extra term, let me just like pop it in there. But the problem is they're not orthogonal, like the fancy way of like B1 is not 90 degrees to ER or E theta. It is to B3, so that works. So the main thing here is kind of like when we draw this B1, if that's theta, I need to figure out like, let's redraw it as like purple. I like purple. I need to figure out like what the components are to get to a step along ER, something less than 1, and then a step along E theta here in the negative direction. So it will be some negative E theta and some positive ER that goes to the same spot as like that x-axis. So we're doing like some trig or something, trig, geometry, witchcraft, just like put the candles out, draw a pentagram, and then like wish for the angle, wish for those numbers. But the price will be steep. So this is one way to do it. We can do it this way. So let's see, if that one's theta, then this angle has got to be theta minus 90, and this one's got to be theta. Does that make sense? Did I do everything right for that triangle? I think so. So this is cosine theta. This is sine theta. So B1 is cosine theta ER minus sine theta E theta. So now I can at least get everything into one coordinate system and then do the cross product that way. I think I grabbed those correctly. Kind of plopping everything in. Then we can do the same thing for that V0 term and add it to the ER and the E theta terms. almost down. All right, here, I'll try it, you try it, we'll see where we end up. And I think I got my terms in there. I think I did those right. I think I did this. I mean, you can check, you're checking my math too, but it's hard to do it on the fly up in front of an audience. So we definitely still have this same term. Like that one should be there regardless, right? Because just because we change the, we change like where our reference frame is. But then there's these other terms in there. So one question here is like, can those be constant? Is there any way for us to say like this is a constant value? Why not? I immediately saw a head shake, like no, this can't be constant. Yeah. So first off, cosine, sine, like those, we have some function, like theta is changing. Sometimes there's some weird stuff, like as you get in, if you ever like keep keep doing this kind of stuff, end up in like partial differential equations. You can have like weird cosine times sine is always equal to 0 sometimes for infinity. Why else can't it be 0? There's one like big glaring factor. Yeah. There's t. The fact that there's a t right there, t is anything like from 0 to infinity, and those terms like they have to change because they're always linearly dependent on time, and that's because we keep increasing the space between them. We can, if we take a derivative of this, like with respect to time, then, yeah, there's some stuff, but we get like a V0 r theta dot and that cosine theta, and then minus that V0 squared. I mean, there might be some other terms, but there's some other stuff. But that'll tell us like what is the moment created on our fixed reference frame. I know we're over time, sorry about that. But over here, like the fact that this system has to move in a straight line, but it's moving, that's creating torque. Somehow there's a torque created. Either the frame itself is on a track and the track is preventing motion, or if this is like, if this is a crane kind of system, as it's coming up, it's the torque around that crane, like as it's changing position. So all of this is like real, it's the real, like what are the constraints being created as it's moving along. Okay, thanks a lot. Next time we'll do something, a new problem, we'll move on, because we checked off all the boxes. Sorry?
So the quiz was supposed to be yesterday.
It was due yesterday?
Yeah.
Oh, I gotta move that then. Yeah, we haven't done that at all.
It's not
Yeah, it doesn't exist. All right, so quiz 4, I'm just like giving a record. Quiz 4, I'll change due date so we can actually build it, and then we'll be able to turn it in.